this is 12.1a on finding the Fourier series representation of a piecewise function. Okay, and I know it looks a little bit weird, but it's really not that bad, and I actually really like Fourier series, so hopefully you guys do too. So we're given the base format for a Fourier series. It's going to look like this. A naught over 2 plus the summation, infinity n equals 1, a sub n cosine pi, in x plus, I don't think I can, maybe I can just like scooch. I don't know if that's enough room. I don't think it is, but I'm gonna force it. N equals 1 of sine pi in x. Okay, we all know what that says. So that's the base formula, base format of what your Fourier series representation is going to look like. And for these coefficients here, we also have formulas to solve for them. In fact, I forgot the one that goes there. It's a b sub n. Okay, so let's start with finding our a naught. Okay, this one's the easiest. So this starts with 1 over p times the integral of negative p to p of just your function x. Okay, and since our function is piecewise defined, we have to break that up. And our p is 1 in this case, which is really nice. It makes the numbers work out nicely. So we have 1 times the intervals from negative 1 to 0, because that's the first section of our piecewise continuous function, of x dx, and then plus the other half of our function, 0 to 1 of 1/2 dx. Okay, so now taking the integral of these, you should get 1/2 x squared evaluated at 0 and negative 1, and then plus 1/2 x evaluated at 0 and 1. And I will say, for not particularly this step, but for these types of problems, be careful with your signs. It's super easy to lose track of where you're supposed to be since you're evaluating so many different little functions. Okay, so we have our 1/2 x squared evaluated at 0, gives us 0, and then minus our 1/2 x squared evaluated at negative 1. So our negative 1 goes positive, minus 1/2, and then plus 1/2, and then minus another 0. So your a sub naught goes to 0, which is nice. One less thing we have to keep up with. Okay, so I'm going to erase all this, and then we can start on the other terms. Okay, so now we know that our a naught equals 0. Okay, so let's start with our a sub n. Okay, so similarly, it's defined as 1 over p times the integral of negative p to p of f of x, but then times our cosine of pi in x dx. Okay, so for this function, which is still piecewise defined, we're going to write it like this. Negative 1 to 0, negative 1 to 0, we have our function x times our cosine, and plus the other half of our function, which is just a 1/2 cosine pi in x. Okay, so taking these integrals, this one is on your sheet, which is really nice, fun story. I actually didn't see the sheet, and so I did these all manually, and then I realized that you guys don't want to see it manually. You want to see it the way it's supposed to be on your test, which is with the nice sheet Dr. Norton provided, so we'll be using that. So we have x cosine, So let's go and look. So for our x cosine, we're going to be using this formulation right here. You might be tempted to use stuff like this over here, and you absolutely can, but you need to make sure that your integral matches the type that you're dealing with. So here you have a definite integral from 0 to p, not from whatever we're looking at now, which is p to 0. So feel free to use this as a reference, but unless it's the same thing and you're not comfortable with the understanding of how that's going to affect this answer over here, I highly suggest just plugging it in to this little guy right there. Okay, so using that for this function, we get our a sub n equal to 1 over n pi, and then times x sine n pi x plus 1 over n pi cosine n pi x. Okay, and this function is being evaluated at -1 to 0. And then we still have our cosine over here, so we're going to get 1 over 2 pi n times the sine of n pi x evaluated from 0 to 1. Okay, so now we are going to look at how these functions behave at these points. So we're going to start with 0 here. So obviously we have our 1 over n pi. Since we have an exposed x over here, that makes that first term 0. And then we have plus our cosine term. So what happens when your cosine goes to 0? You'll get 1. But don't forget, you also have an n pi on the cosine itself, in addition to the 1 right here. You have that, and now minus your lower bound, which is going to be, so your -1 in your sine. So what happens when x equals -1? So the argument inside your sine is going to equal n pi. So any multiple of pi, sine is going to equal 0. Okay, so now we're just left with our cosine term, which again still has an n pi on it. So what happens when our cosine goes to -1? So then we're left with a cosine with the argument of n times pi. So anytime you have that, you can write something that looks like this. And that has to do with the fact that a cosine on a pi rotation like that is going to alternate between -1 and +1, and that depends on whether this n is even or odd. But for the sake of this class, we're just going to write it like this, and that's going to be good enough for us. Okay, so condensing this, we get that our a sub n equal to 1 minus -1 raised to the n over n pi squared. Okay, and the only thing I did to combine that is I multiplied this term right here by 2 over 2, but for the lack of space, I just went ahead and condensed it. If you're confused on that step, please let me know. You know what? Never mind, forget about that. That's actually for next step. You can just combine these like normal. Okay, so now we have our a sub n. Go ahead and write it up here. Get 1 minus negative 1 to the n, then over n pi squared. Okay, so I'll go ahead and get rid of all of this so we can start on the last coefficient, which is our b term. Okay. I guess that's good enough. Okay, so now for our b sub n. So for our b sub n, it's a very similar formula. You have your 1 over p times your integral of negative p to p of your function x times sine pi n x dx. Okay, so when you start plugging in values for this, you will get 1, so that's your 1 over 1 for your p. Keep an eye out because it's not always 1, so you might actually have to be multiplying by something. Times your f of x, which in this case is x times sine pi n x dx, and this is going from negative 1 to 0, so that's what it is on our piecewise function. Now we're going to add the rest of our functions, 0 to 1. Now we have our 1/2 sine n pi x dx, and we can start integrating now. So this also has a chart entry, so you don't have to worry about integration by parts or anything, so that's super nice. So we're going to come over here, and again, keep in mind you're not going from 0 to p, you're going from negative p to 0, so you can't just plug it in directly unless you feel really comfortable understanding how switching the parameters like that. I know I don't, because I would rather just do the little math in between to make sure. So just keep that in mind. So we're going to look at that chart to solve for our b sub n. So we know that it's going to look like negative n over pi times x cosine n pi x, and then minus 1 n over pi sine n pi x. And this is all being multiplied by that first thing there. So and this is being evaluated at our negative 1 to 0. And we can't forget about our second less problematic part over here. That's actually going to be a negative, so we'll go ahead and write it that way. So minus 1 to pi n, and then our cosine n, well, pi n x, and this one is being evaluated from 0 to positive 1. Okay, so when we start the evaluation, we're going to obviously start at 0, and since we have this exposed x, we have our negative n pi, and then times 0 here. And then evaluating our sine term at 0, we should also get 0, being that the sine of 0 is 0. So minus 0 here, and then plus, well, I guess minus, sorry. And then minus our lower bound. So what happens when we plug in a negative 1 to our cosine? So don't forget about this negative 1 right there. So we have a negative 1 times our negative 1 to the n that we got from the cosine term right there. Okay, and then when we go to evaluate our sine term over here, since it's just going to end up as n times pi, that is also going to go to 0. Okay, so you should end up for your b sub n, well, the first part anyway, is something that looks like this. And don't forget about what you have going on over here. So now let's evaluate this. So 2 pi over n, and then times our cosine evaluated 1. The cosine evaluated 1 is going to give us another negative 1 to the n. Okay, and then our cosine evaluated at 0 should give you a 1, just because the cosine is 0. Those are super hard for me to remember, and every time I say it in the video, I have to look at a little list of where I have it written down. I don't know why. I can never remember that. Okay, so we have minus a 1 for the cosine of 0. Okay, so maybe I can scooch this down a little to give us a little bit more room, so hopefully we can solidify our b sub n term. Okay, so this is where the multiplying by 2 over 2 comes in, but you should get negative 1, negative 1, n plus 1 over 2 pi n, and then minus negative 1 to the n over n times pi. Like I said before, multiplying by 2 over 2 allows you to combine these terms, and you should get b sub n equals 1 minus 3 times negative 1 to the nth power over 2 pi n. Okay, and so now we have all that we want, all that we need to actually write the problem in a format that Dr. Noyes is looking for. So I'm going to get rid of all this and I'll write the answer, and that will be the end of this problem. Okay. I don't know why that bothers me. Okay, so we know that our general format, which I wrote up here, looks like this. So we can now say that our f of x equals our a sub 0, which we decided is 0, so we don't really need to include it, times the summation of n equals 1 going to infinity of our a sub n, which is 1 minus negative 1 n over n pi squared, and then times our cosine terms, n pi x. Okay, and then plus the same summation. You can combine these if you want, but for the next problem, we're going to need them separate, so it's not super imperative that you combine these summations here. So, and then for our b sub n, we got 1 minus 3 negative 1 to the x over 2 pi n. Okay, and then times our sine n pi x. Okay, and that is the solution to this problem. I hope it made good sense. Let me know if you have any questions or you need help understanding the chart, because hopefully the calculus isn't the super hard part of this, and it's just the evaluating and understanding how these trigonometric terms act at those boundary conditions. Okay, so let me know if you have any questions, and I'm absolutely here to help you guys if you need anything.